Hi, thank you very much. It's a pleasure to be here. So I'm going to talk about the mathematical aspects of a problem originating from structural biology. And the problem is the problem of deciphering the three-dimensional structure of large molecules. The standard method to do it is called X-ray crystallography. In this method, you take many copies of the same molecule, you pack them together in a form of a crystal, and you project a beam of X-ray and you study the diffraction pattern. The problem is that many interesting molecules do not crystallize very well, and people are looking for alternatives. And one of these alternatives is cryo-electron microscopy, by which you are trying to investigate the three-dimensional structure by studying the images that you get from an electron microscope. So let me draw for you a schematic picture of the experimental setup. So an electron microscope is a tube which projects a high-energy beam of electrons, and downstairs you have a thin plate of ice consisting of multitude of identical molecules immobilized in random orientations. Now the beam interacts separately with each of these molecules, and the molecule is destroyed as a result of the interaction, by the way, because the organic material is very sensitive, and you pick up a projection image which encodes the diffraction pattern. So in this way you end up with a collection of images, each associated with a different molecule in the solution, and the goal is to take this collection of images and to reconstruct from them the three-dimensional structure of the basic molecule. Now there are two main difficulties involved. The first difficulty is that these images are very noisy, and this is a very severe difficulty. And the second difficulty is that you don't know the orientation which produced every image. So I'm going to focus on the second difficulty, but everything that I'm going to tell you about it is also relevant to the solution of the first difficulty of the noise. Okay? And I'm going to comment about it in the end. So in order to specify the mathematical model, I will need the following terminology. So I will denote by VR the three-dimensional Euclidean vector space. So V is just R3 with the standard inner product. And X is the frame manifold associated to V. So a point in X is just an orthonormal basis, E1, E2, E3. So this is the picture. This is a point in this manifold. So this is E1, E2, and E3. And the third vector is special. I will denote it by pi of X and refer to it as the viewing direction. So this is pi of X. And the terminology will be clarified in a moment. And the last piece of terminology is to associate to every frame an orthogonal embedding iota x, to every frame x iota x from R2 into V, which sends a pair of coordinates PQ to the vector PE1 plus QE2. So I'm using the first two vectors of the frame in order to embed the standard plane into the three-dimensional vector space. So now the model, so the mathematical model behind this picture. So it's more convenient to think about a single molecule fixed in space and observed by an electron microscope from various orientations. So the orientation is associated with the microscope instead of with the molecule. Just it's more easy to think about it like that. So under this convention, the molecule is modeled by a real-valued function phi on the vector space V. If you wish, this is the volume function of the molecule. So here is the molecule. It is modeled by a function. And an orientation of the microscope is modeled by a frame x in x. So this is the viewing direction. This is where your eye is located. And these are the coordinates of the camera. The microscope comes with a fixed coordinate system. And the projection image that you pick up when observing the molecule from an orientation x is a real-valued function ix on the coordinates of the camera, which is given by the radon projection of the potential function along the viewing direction. So pictorially, the intensity of the pixels are correlated with line integrals along lines which are parallel to the viewing direction. So this is how the image is modeled mathematically. And overall, the data that you collect from the experiment is a finite set of projection images, which are labeled by frames. Okay? So X runs in a finite subset of the frame manifold. And the goal is to take this collection of images and to reconstruct from them the potential function phi. Now, it's very important to note that at this point, we don't know the frame associated with every image. So for us, the label X is only a suggestive notation which reminds us that every image is associated with a particular frame. If we knew the frame, then we could place every image in its appropriate place in the three-dimensional space and reconstruct the potential by applying the inverse radon. So in this regard, so this is only a suggestive notation. It's a label for us. But remember, it represents a frame. And in this regard, the main computational problem is to compute for every image its corresponding frame, or more precisely, the orthogonal embedding associated with this frame. So let me summarize everything in a picture. We have a collection of images, which are just a bunch of R2s equipped with functions. And we know that each image is embedded in a certain way inside the three-dimensional space. And we are trying to compute these embeddings. And then we solve the problem by applying the inverse radon. Okay? But the only thing that we are given in this is this collection of R2s with images. So the computation proceeds in two steps. In the first step, you extract from the images certain geometric data called the common line data. And I can summarize this procedure in one diagram. So say we have two frames, x and y in x. So we have the vector space V. We have one copy of R2 and another copy of R2, one embedded via iota x and another embedded via iota y. And the images of these two maps are two planes inside V, they intersect in a line. This is called the common line. Now here we have the potential function phi, here we have the radon projection Iy, and here we have the radon projection Ix. Now you can compute the three-dimensional Fourier transform of phi. You can compute the two-dimensional Fourier transform of Iy and the two-dimensional Fourier transform of Ix. And the claim is that these two functions are the restriction of this single function to these two planes respectively. This is called Fourier slicing property. And it's just the fact that Fourier transform interchange restriction with integration. So this is just a fact. But it has an important meaning, because it means that you can use these two functions, which are in fact given to you, these are the images, in order to calculate, in order to identify the two coordinate realizations of the common line. How do you do it? You just look for a pair of directions here and here on which these two functions have high correlation. You look at this pair of directions and these give you the identification of the common line. So this is equivalent to saying that you can use these two functions in order to compute a 2x2 matrix, which I will denote by Cxy, which give you this identification. So this matrix just sends this vector to this vector, and it is 0 on the orthogonal direction. Okay? And theoretically, this matrix is given by the following formula. You first go via iota y to here, you project on the common line, and then you go via iota x transpose back to here. So the understatement is, the statement is that you can use the images in order to compute the matrix relating the corresponding frames. So from the images, we can compute this collection of matrices. And this is called the common line data. So again, let me summarize the situation. We have the images, and what we see that from the images, we're able to compute for every ordered pair of images a 2x2 matrix. The 2x2, this is called the common line matrix. So for every ordered pair of images, we can compute from the images that the 2x2 rank 1 matrix, which is the common line matrix between the corresponding frames. So although we don't know the frames, we are able to compute from the images certain non-trivial binary relation between the frames, which is given by these common line matrices. Okay? And now the algorithm, which I want to explain. So what the algorithm does, it accepts as an input the common line data and produces an output the orthogonal embeddings. So the input is so this is the intrinsic reconstitution algorithm. It accepts as an input the common line data and produces an output these embeddings that we want to compute. And what the algorithm does, this is the main idea. What the algorithm does, we compute from the common line data a three-dimensional Euclidean vector space that is very different than the vector space V that we started with. And then we solve for the embeddings in the coordinates of this new vector space. Okay? And this will constitute a solution to the computational problem in the sense that what we computed is not equal to what we wanted to compute. We are trying to solve for the iotas. It's not equal because it's a new vector space, but it is isomorphic to what we wanted to compute. So the output of the algorithm that I'm going to describe is not an element of a set, but an object of a category. This is just some abstract perspective about what you are going to see. But everything is going to be very concrete. So the algorithm proceeds in 3 steps. The first step, we define the following vector space, Hn, which is just R2 valued functions on the set of labels. Remember, the images are labeled. So I'm just considering R2 functions on the set of labels, and if you order this set, this is just R2 to the n. Okay? Second step, we define an operator on this vector space using the common line data. So this is Cn from Hn to Hn. And this operator is defined as follows. It takes a function and sends it to a new function whose value at the point x is 1 over n, n is the number of images, sum over y in xn, cxy, f of y. So I'm using the common line data to define an operator on this vector space. And if you want to be really concrete about it, this operator is given by the following matrix. It's a 2n by 2n matrix, where in the ij place you put cxi xj. So this is a 2n by 2n matrix, which you build out of the common line matrices. Okay? And finally, and this is the first step, and this is the core of the algorithm.
What's x in sum big sub n? X and big sub n?
Y, x, here?
No, you sum over what again?
You sum over xn. Xn is the set of labels. Remember, the images are labeled by frames, and this is just the set of labels. Okay? So, and the first step is the computation of this model of this three-dimensional vector space and the solution of the embeddings. So the first step is the construction of the model. So we have to cook up a three-dimensional vector space, and we do it as follows. Cn acts on Hn, and this is in fact a symmetric operator, so it induces spectral decomposition, Hn lambda. And we define the following vector space Vn to be the following portion of the spectrum, sum over lambda greater than 1 over 3, Hn lambda. And this 1 over 3 is not special in any manner. The only attribute which I want to record it is that it lies between 1/2 and 1 over 12. Now, these two numbers have theoretical meaning. This is, in fact, the maximal eigenvalue of this matrix when n goes to infinity. I'm going to explain it in a moment. And this 1 over 12 is the second highest eigenvalue of this matrix when n goes to infinity. So, in fact, what we do, we pick the highest portion of the spectrum, the part of the spectrum which belongs to 1/2. You're going to see it later. And this is a spectral gap, which can be proven, of course. And this gap is very important because this is what is responsible for the numerical stability of the algorithm. Okay? So we are computing a vector space which is well defined numerically because there is a spectral gap here. And first theorem that I will have to justify for you is that indeed this vector space is of the right dimension, namely the dimension of Vn is equal 3. So this is a three-dimensional vector space, very different than the vector space V that we started with. And now we want to solve for the embeddings inside this vector space. And we do it as follows. We have Vn. It lies inside Hn. True? Of course. Pick a label x in xn. So we have the orthogonal projection on the x copy of R2, because this is just a direct sum of R2s labeled by these elements of this set. So take the composition and denote it also by projection x. Now this is Euclidean vector space, this is Euclidean vector space, so you have a map in the opposite direction, which I will denote by phi of x, which is just projection x transpose. And this is a map from R2 into Vn. So what we established by this construction is a three-dimensional vector space together with collection of maps phi of x from R2 into Vn. And the upshot is the problem is solved. In what sense it is solved? It is solved in the following non-trivial sense, and this is the paradigm of categorical optimization. It is solved in the following sense. This is the content of the following theorem, that this object is isomorphic to what we wanted to compute in the following sense. There exists a unique isometry. I will have to prove this theorem, or at least explain it, justify. There exists a unique isometry, which I will denote by tau, from the vector space V that we started with to the vector space Vn that we ended with, so that for every R2, for every x in xn, we have the iota x that we wanted to compute, and we have the phi of x that we actually computed into this vector space, and the claim is that this diagram commutes for every such label. So if you believe the existence of such a tau, it means that if we constructed this side, it determines this side up to a global action of OV. If you believe that such a tau exists, this means that if you know this side, it determines this side up to an action of a fixed element here. Which means that in fact what we computed is all the iota x up to one global rotation. Which means that we can reconstruct the molecule up to one global rotation. So you see that in fact we are computing an object. This is not an element of a set. This is an object of a category, and this is just the statement that it is isomorphic to the object that we wanted to compute. Okay? So just keep this in mind. So now the mathematical explanation. How much time I have?
10 minutes.
Okay, so the explanation, I will rush. I just want to give you an idea about what is going on here. So this should look very mysterious, I hope, because it's really mysterious. It's a different kind of approach to nonlinear optimization. And so here is the explanation. So the explanation is based on considering the continuous limit of the algorithm when the number of images goes to infinity. So what happens in the limit? The configuration space xn converge, if you wish, measured theoretically to the frame manifold. And here I'm assuming that the molecules are distributed independently and uniformly at random. So this thing converges to this. The Euclidean vector space Hn, R2 valued function on the set of labels, converge to the infinite space H, which is R2 valued functions on X. The common line operator converges to an integral operator from H to H, whose kernel is just the common line matrices, the same kernel. And this model that we constructed, which is the highest portion of this finite operator, converge in the limit to the maximal eigenspace of this operator. Okay? And what is the gain in moving to the continuous site? The gain in moving to the continuous site is that new structure emerge, and the structure that you see here, which you don't see here, is an action of SOV, the special orthogonal group, which acts on the frame manifold just by rotating the frames, and consequently also acts on R2 valued functions on X. And what we are going to do, we are going to use the representation theory associated with this action in order to interpret this vector space and consequently explain the algorithm. So the main fact that which we are going to use is the fact that the common line operator, this operator C, in fact commute with the SOV action. C composed with G is G composed with C for every G in SOV, and this is very easy to verify. It's an intertwiner. And this is important because this enables us to interpret the spectral decomposition of C in terms of the irreducible decomposition of this representation. So we are going to give this interpretation, and this will give meaning to this vector space. So namely, what is happening here is that SOV acts on H. This is a compact group, and it induces the composition into irreducible representations. So sum over n from 0 to infinity, Hn. So this is the irreducible representation of SOV of dimension 2n plus 1. And because C commutes with the SOV action, it preserves each of these components. This is a tautology in representation theory. And moreover, if you restrict C to each of these components, it must act as a scalar because each of these components is irreducible. This is called Schur's lemma. So in fact, let me summarize everything in a theorem. If you restrict C to Hn, first of all, it can be restricted because it preserves each of these components, and it acts as a scalar lambda n identity. And the claim is that this scalar, it can be computed again using techniques from representation theory, is minus 1 to the n minus 1 over n times n plus 1. So these are in fact the eigenspaces of C. These irreducible components are the eigenspaces of C. Okay? And now what are the consequences of this theorem? Many. So first consequence is using this formula, you see that the maximal eigenvalue of C is what? Is n equal 1, 1/2. The second highest positive eigenvalue is n equal 3, 1 over 12. So this is your spectral gap, and these are the numbers that I described before. Moreover, you see that the maximal eigenspace, from the point of view of representation theory, coincide with H1, with the irreducible representation of dimension 3. This is the maximal eigenspace. So indeed, the dimension of V is equal 3. So the highest portion of the spectrum that we picked in the discrete scenario is indeed of dimension 3. So this justified what we did. But we see something more in the continuous setup. We see that what we in fact computed is not only a three-dimensional vector space, and by that something isomorphic to V, but something which is isomorphic to V as a representation of SOV. So the situation is much more rigid. And now let me explain the algorithm. So here is the explanation. The explanation is quite transparent, very direct. What is the mathematical structure which underlies the intrinsic reconstitution algorithm? So this is it. We have the vector space V. It lies inside H. For every frame X, you have evaluation morphism into R2, just taking an R2 valued function and evaluating it at X. This is this orthogonal projection in the discrete scenario. You can compose, let's denote the decomposition by projection X. We have a map in the opposite direction, phi of X, projection X transpose from R2 into V. Clearly, the limit of Vn with its finite set of phi of X converge to V with this infinite collection of phi of X. And now the justification of the algorithm, the second theorem that I told you about the existence of tau, is the consequence of the following theorem, which I'm going to prove because the proof is one line. There exists a canonical, now not unique, canonical because I'm going to describe it to you, isometry tau from V, the old vector space V, into V, such that it commutes between the phi x, which I defined using these things, with the iota x. If I prove this theorem for you, This justifies the theorem in the discrete scenario. Okay? And let me prove it, because this is the mathematical structure underlying the algorithm. And this structure now we know how to generalize it and build more sophisticated algorithms solving other problems. So here is the proof. It's one line, so I can do it. So I'm going to construct this tau. Let me do it. First of all, I define it from V into H. How do I do it? In the only way possible. I'm sending a vector V. I have to send it into an R2 valued function, tau of V. This is R2 valued function on X. So let me tell you who is this function. Tau of V at the point X, I should give you a vector in R2. So I just take iota X, transpose, apply to V. This is an element of R2. So this is the function. I defined for you a map from here to here. Now this map is very natural, and you can check that in fact this map commutes with the SOV action. You have an SOV action here. You have an SOV action here, the representation, and the claim is that this map is an intertwiner. It commutes between the SOV action here and the SOV action here, which means that the image of this map must be isomorphic to V. But we know the irreducible decomposition of this H. And who is the only copy? This is the three-dimensional representation of SOV. There exists a unique copy of such a representation here. So the image of tau must be H1. This is the unique copy. But we know that H1 is V. So in fact, tau is a map from V to V. And it must be an isometry up to a scalar, because these are irreducible representations. And why tau satisfies this property? Well, this is the definition. And you are done. And this is the structure. So the structure of the algorithm is just a natural realization of the vector space V inside R2 valued function of the frame manifold. Which, and let me just make another small emphasis. So the object is this vector space. Is this H1, which is characterized using representation theory. And then the algorithmic approach is just the technical statement which tells you that you can compute this object using an operator which you can cook up from the images. And in fact, now we know that we can compute the same vector space using other operators, which you cook up in different ways. Operators which in fact do not depend on the uniformity assumption of the molecules. So you can solve the same problem without assuming that the molecules are distributed independently and uniformly at random by computing the same vector space using a different operator. But all the time it's the same vector space that you are computing. And you are using this structure in order to establish the solution. I think I'm going to stop here. Thank you.